You know that little zap you feel on a dry day? That crackle when you take off a sweater in the dark? Yeah, we've all been there. But what is that spark really? Today, we're going to dive into the secrets of static electricity. And trust me, what we find is pretty shocking.
I mean, you know exactly what I'm talking about, right? It's a dry day, you pull a sweater over your head and you hear that crackle. Or maybe you slide out of your car, go to touch the door handle, and bam, you get that zap. Well, that tiny shock, it's way more than just annoying. It's actually a clue, a tiny glimpse into one of the most powerful forces in the entire universe. And it all boils down to this thing called electric charge.
So how in the world did we even begin to figure this stuff out? Well, the whole story starts with some surprisingly simple experiments. You can almost picture these early scientists, kind of like detectives on a brand new case, noticing that if they rubbed certain things together, they'd get these strange new powers. And their very first big break? It came from a couple of really basic rods.
So, here's what they did. They take something like a glass rod and rub it with a piece of silk. Then they take a plastic rod and rub it with some fur. And when they brought these electrified rods close to each other, something amazing happened. A clear pattern started to show up, a kind of constant dance of pushing away and pulling together, repulsion and attraction. And this simple little dance led to the very first fundamental rule of electricity. If you had two charged glass rods, they'd push each other away. Same thing if you had two charged plastic rods. But if you brought a charged glass rod near a charged plastic rod, they'd pull right towards each other. The conclusion was just unavoidable. Like charges repel and unlike charges attract.
Now, this might sound simple, but that behavior, that whole push and pull thing, was a massive revelation. It was a huge clue. It told scientists something absolutely crucial. There couldn't just be one kind of charge. It just wouldn't work. To explain this constant dance of attraction and repulsion, you had to have at least two different types.
And guess who we have to thank for the names we still use? None other than Benjamin Franklin. He's the one who looked at the charge on the glass rod and said, let's call that positive, and the one on the plastic rod, we'll call that negative. Honestly, it was a totally random choice. He could have called them A and B, but the name stuck, and here we are today.
Okay, so you might be thinking, if there's all this charge everywhere, why aren't we getting zapped constantly? Well, that's because most of the time, things are electrically neutral. Now, that doesn't mean they have zero charge. Oh no, it means they have a perfect, beautiful balance of positive and negative charges, and they just cancel each other out.
So where does that spark actually come from? Here's the key. You don't create charge out of thin air. You just move it around. Think back to that glass rod and silk. When you rub them together, these tiny negative particles, we call them electrons, are literally ripped away from the glass atoms and they jump over to the silk. So now the glass rod is missing some negatives, which leaves it with a net positive charge. And the silk, it's got all those extra electrons, so it's now got a net negative charge.
All right, so we've got a handle on what charge is. Now we get to the really cool part. It turns out that there are three, let's call them golden rules of charge. And these rules are fundamental, they're unbreakable, and they don't just apply in some fancy lab, they govern how charge works everywhere in the entire universe.
Rule number one is thankfully super simple. It's called additivity. And it just means that if you want to figure out the total charge of something, you literally just add up all the individual charges. That's it. You treat them just like regular old numbers.
So, for example, let's say you've got a system with a charge of +2, another piece with -5, and a third with +4. You just do the simple math. 2 minus 5 plus 4 equals +1. The total charge of the whole system is +1. Yep, it really is that easy.
Okay, rule number 2, conservation. This one is a huge deal in all of physics. Basically, it means that charge can't be created or destroyed. You can't just snap your fingers and make charge appear, and you can't make it disappear into thin air. Remember our glass rod and silk? The total amount of charge was the same before and after they were rubbed. All we did was move it from one place to another. It was just redistributed.
And now for rule number 3, quantization. And this one is probably the weirdest, most mind-bending of the bunch. What it means is that charge isn't like water flowing smoothly. Nope. It comes in tiny, individual little packets. The smallest possible packet of charge has a name. It's called the elementary charge, or just E. And here's the crazy part. Every bit of free charge you will ever find, anywhere, is a whole number multiple of this single tiny unit. And when I say this packet is tiny, I mean it's almost impossibly small. The value of E is about 1.6 times 10 to the negative 19th coulombs. I mean, that's a decimal point followed by 18 zeros and then a 16. It's so ridiculously tiny that in our day-to-day lives, we just never notice it's made of individual steps. To us, it just feels totally smooth.
You know, a really good way to think about it is like a dotted line. If you're standing far away, it just looks like a solid, continuous line, right? But if you walk right up to it, you can see it's actually made of a bunch of separate individual dots. Well, electric charge is just like that. On our big human scale, it seems smooth. But if you could zoom way, way in, you'd see it's actually grainy. It's made of these distinct little packets.
So let's just pause for a second. We started with a simple spark from a sweater, and now we're talking about the fundamental rules of the universe. So why should you care? What's the big deal? Well, it's because this force isn't just about static lane or getting zapped by your car door. It turns out it's about, well, pretty much everything.
This very same force, this attraction between positive and negative, it's what holds atoms together. It's what holds molecules together. You know why glue is sticky? This force. You know how some insects can walk on water? Surface tension, which is caused by this force. It is, and I'm quoting here, all-pervasive. It is literally the force that holds our entire world together. Heck, it's the force holding you together right now.
And that's what's so incredible. It brings us right back to where we started. That little shock from your sweater, it isn't just some random, annoying thing. It's a tiny personal reminder, a little demonstration of the exact same fundamental force that builds molecules, that holds matter together, and that ultimately makes life itself possible. How cool is that?
So here's a final thought to leave you with. Everything we've talked about today has been about static charges, charges that are basically sitting still. But what happens when those trillions upon trillions of tiny charges stop sitting still? What happens when they all start to move together, to flow on a massive scale? Well, that's when you get lightning. That's when you get the electricity that powers our entire civilization. But well, that's a whole other